So what should we do if the lead time is not exactly L periods? In other words, demand and supply are now uncertain. So our intuition should tell us that if we have now more uncertainty, this is going to lead to more safety stock. And that intuition is correct, but let's look at the math behind it. So if we said the lead time is not exactly L periods, we still have demand that is stochastic or is governed by a distribution. And so we would be given, just like before, the average demand per period and the standard deviation of demand per period. But we also now need to incorporate the uncertainty of the lead time. And so in the past, we just considered L as the average lead time and the standard deviation of lead time was 0. But now we want to consider, what if the standard deviation of lead time is greater than 0? And so what we would do here is we're going to calculate, just like before, the two most important parts of inputs to the R and the safety stock, which is the expected demand during lead time and the standard deviation of demand during lead time. So as you'll note, the expected demand during lead time, as long as the lead time on average is L, what we would expect to happen, even though sometimes it'll be more or less, on average, it's still D times L. But what changes is the standard deviation of lead time demand. And so as you can see in this equation, we now have another term, a plus term on the standard deviation of lead time demand. So in the past, our S of L, or standard deviation of lead time, was 0. And so that term went away at the end, and it was just the square root of L times the standard deviation of standard deviation of demand per period. But now when we have standard deviation associated with the lead time, we add to that, which means the standard deviation is going to go up, which means our safety stock is going to go up for the same level of service. If you're interested in derivation, this derivation is taken from the textbook Inventory Control by Exeter. And I won't go through all the details other than to state the derivation comes from deriving variances, which again are additive, not standard deviation. So you can see the space that we're deriving that equation is in terms of variances. So let's use that equation. And so if we think about the average demand per day, if we're given that as D of 2,500, the standard deviation of demand per day of 500, and then the average lead time for replenishment is L of 7 days, which is what we've all done in the past, but now we say it's not exactly 7 days. There's actually a lot of variance. So in this example, our standard deviation of lead time is also 7 days. And so we are going to answer 3 questions. The first is, what is the mean demand during lead time? The second is, what is the standard deviation of demand during lead time? These are the 2 key things that you always need to figure out if you are asked for safety stock and reorder point. And so once we have those, and then we incorporate our cycle service level, we can calculate the safety stock. So in terms of the first question, expected demand during lead time, expected values operate like we would like them to. And so here, if we have 2,500 per day, and on average, the lead time takes 7 days, then we would expect, on average, 17,500 units to be demanded during lead time. So again, lead time is when I place the order to when it shows up. And yes, that lead time will vary. It won't be exactly 7 days, but on average, we will experience 17,500 units of demand. The second question, what is the standard deviation of demand during lead time? This is where we need to use this new equation. Okay, this new equation for the standard deviation of lead time demand that incorporates that demand is uncertain, but also supply or the lead time is uncertain. And so if we plug in these numbers, here we can see that we also got 17,500 is the standard deviation of demand during lead time. One thing to note is that if the standard deviation of lead time was 0, if this S of L was 0, this part of the equation here at the end would go away and we'd have what we did before. And so this equation you could think about is a more general equation that if you set this to 0, the second part under the square root would go away. And so now we want to ask our question, okay, great. We have the demand during lead time distribution. We have that they're mean and standard deviation. If we know that they're normally distributed and we want a cycle service level of 90%, now we can calculate the safety stock. And because it's normally distributed, we can use the equations that safety stock is Z times the standard deviation of lead time demand. We just calculated that, the standard deviation of lead time demand. So the only thing we have left is to calculate Z. You can either go look up 90% on a Z table, a normal standard table, or use Excel, and you would find that Z is 1.28, and therefore our safety stock in this example is 22,400 units. One thing to note is if the lead time was exactly 7 days, the safety stock would go down for the same service level. So still having a cycle service level of 90%, we need less safety stock. And so this is just another example in this class where variability comes in, and variability causes us to be less efficient with our resources. And so here we're less efficient with our inventory. We need more safety stock for the same service level. And so, just to get some kind of intuition is what happens to safety stock when lead time becomes more uncertain. Your intuition should be that as the standard deviation of lead time goes up, what else happens is our demand during lead time uncertainty increases, so that goes up, and that means safety stock must also go up. And so if we do this a little bit more mathematically by plugging in some information here, so this table uses the data calculated from before, uses this equation, and what is changing is the standard deviation of lead time demand. So everything else is staying the same. And what you can see here is if nothing else changes, we still have the same cycle service level of 90%. As this goes up, the standard deviation of lead time goes up, our standard deviation of lead time demand goes up, and our safety stock goes up. And so as we have more uncertainty, we need more buffer. We need more inventory here in the form of safety stock to meet the same service level. And so the big picture takeaway from this is that a reduction in supply uncertainty can help to dramatically reduce the required safety inventory without hurting product availability. So here's one more mathematical example of reducing variability, reducing uncertainty will make for a more efficient supply chain.